A camera lens captures photons. A microphone records air pressure. Physical reality enters a machine as entirely separate chaotic data streams. To process these raw inputs, deep neural networks compress pixels and audio waves into standardized, high-dimensional mathematical vectors. This is the primary hurdle for multimodal large language models. Multimodal large language models, or MLLMs, are AI systems designed to process and reason across text, images, and audio simultaneously. Their core objective is semantic synthesis. To analyze sight, sound, and text at the same time, the model requires a unified mathematical space where these disparate data types can coexist. Early artificial intelligence systems processed a single data stream at a time. An image classifier was blind to text, and a language model was deaf to audio. Without a shared mathematical framework, an AI might recognize a picture of a dog and the sound of a bark, but it cannot resolve the fact that both inputs refer to the same object. The barrier to creating that shared framework is a geometric bias known as the cone effect. This phenomenon occurs when deep neural networks naturally restrict the embeddings of a single data type to a narrow, isolated region of the vector space. When engineers initialize separate encoders to process different modalities, the random starting parameters map those distinct inputs into completely isolated regions of the embedding space. This 3D coordinate space plots the outcome. Text vectors clump tightly in one region, image vectors isolate in another. This specific void is the modality gap. Forcing incompatible data into this shared space is AI's central challenge. Solving this requires two interdependent mathematical operations. The first is alignment. Alignment forces different modalities to shift their coordinates until they occupy a shared semantic geometry. The second operation is fusion. Once the features are aligned, the system integrates them to execute complex downstream reasoning. Combined, alignment and fusion allow the network to resolve cross-modal dependencies and execute multi-step reasoning. Early researchers attempted to align data using statistical methods, like canonical correlation analysis. Canonical correlation analysis is a technique that extracts linear relationships between two variables. It fails when applied to the highly nonlinear, complex data generated by deep neural networks. This schematic illustrates the modern solution, a two-tower model. It utilizes two separate encoders, one for images and one for text, processing parallel streams of data independently. The mechanism driving these parallel towers is self-supervised learning. In standard unsupervised learning, algorithms search for hidden structures within data without any target outputs. Self-supervised learning exploits the paired structure of raw web data, like an image and its caption, to generate ground truth labels. It uses a contrastive objective function. In the latent space, the math pulls a matching image-text pair together while pushing a non-matching pair apart. This continuous pushing and pulling process occurs simultaneously across billions of parameters during pre-training. The system establishes semantic correspondence between words and pictures without a human ever manually annotating a single file. By utilizing the structure of the internet as its own supervisor, the two-tower model solves base alignment without the bottleneck of manual human labor. This equation represents standard softmax contrastive loss. The highlighted denominator exposes a severe optimization bottleneck. It relies on the entire data batch to compute the loss. Softmax requires global batch synchronization. Every single data point in the batch must be mathematically compared to every other data point simultaneously. This all-to-all synchronization creates a memory bottleneck across GPU clusters, placing a hard ceiling on training scale. The mathematical solution that breaks this barrier is sigmoid loss. Sigmoid loss shatters the interconnected grid, treating every single image-text pair as a completely independent binary classification problem. By decoupling the loss computation from the global batch size, engineers can utilize highly memory-efficient chunked training. This stabilization allows batch sizes to scale from the thousands into the millions. Algorithmic elegance, rather than brute force compute, unlocks massive-scale multimodal training. The two-tower model has a distinct limitation. Global vector alignment relies on simple dot products, which cannot execute complex reasoning. Tasks like visual question answering require the model to understand fine-grained spatial interactions between objects rather than just registering a global match. Deep Fusion replaces global concatenation with dynamic token-level integration. This pipeline embeds a trainable Q-former adapter into a frozen large language model. The Q-former extracts targeted visual data from an image encoder. Inside, cross-attention mechanisms use queries, keys, and values to dynamically weigh the importance of incoming visual features and text. The primary function of this adapter is to map non-text visual features into the native text space of the language model. The frozen LLM then acts as a central reasoning engine, ingesting the translated visual tokens as if they were standard language. Because the core parameters remain locked, this pipeline allows the system to ingest video, audio, and images without retraining the underlying language model. Deep Fusion maps raw perceptual features directly into the symbolic logic of the language model. The complete modern pipeline follows a specific sequence: raw data ingestion, contrastive alignment, and finally, adapter-based fusion. Deep token-level fusion introduces severe computational bottlenecks during inference. Look at this grid of scraped web image-text pairs. It illustrates the data paradox. Scaling laws demand billions of pairs, but web-scraped datasets contain severely mismatched and noisy data. Feeding a model noisy, mismatched image-text pairs completely fractures the shared semantic geometry built during the alignment phase. Researchers are deploying hyperbolic entailment filtering to ensure data quality at scale. This is a filtering technique that uses complex geometry to eliminate underspecified or meaningless image-text pairs based on their directional relationships. These algorithms enforce semantic alignment and intramodal specificity before the training phase even begins. Rigorous spatial and semantic alignment is a prerequisite. Fusion fails on misaligned data. Ultimately, coherent training data provides the mathematical baseline required for an AI model to accurately reflect the physical world.